everyone. So we want to continue on with our discussion of energy. So you should have learned some things from that worksheet. Some of the basics of different types of energies and some of the equations we use. Just a quick recap. You should have learned about work, which is usually defined as our ability to change energy. If you do work on something, you're able to change one of the types of energies that an object has. Energy is actually defined as the ability to do work. It's a kind of a cyclical definition. Potential energy, you've probably heard, it's defined as stored energy. Now, there's two different types of potential energy. There's gravitational potential, which is usually caused by raising an object to some height. And then there's spring potential, which is caused by either stretching or compressing something that's rubbery, like a spring or a rubber band. Then there's also kinetic energy, which is usually defined as the energy of motion. If the object's moving, it's got kinetic energy. And then the last one is the thermal energy. This is usually also called heat or energy lost, and it's usually caused by friction. So if you see any of those words, thermal, friction, heat, lost, it's all kind of representing the same thing. And then all these are different types of energies, and they're all measured in the same unit of joules. So it doesn't matter what type of energy we're talking about, it's all joules. And then there are a bunch of equations, most of which are on the reference table for energy. So there's this one, work equals force times distance, or also a change in total energy. Potential energy is mass times gravity times height. P equals 1 half kx squared, so k being the spring constant, x being the how much the spring stretches and compresses. Kinetic energy is 1 half mv squared. Okay, so these two I wanted to mention. There's the total energy equation, which is basically just taking all the energies that we have, potential, kinetic, heat, and anything else, and adding them up. This is slightly different to what's called mechanical energy. Mechanical energy is not on the reference table, and it's something you just need to know. It's strictly potential plus kinetic. The main idea being that with total energy, it's including all the different types of energies, but mechanical only uses the useful energy. Heat is not something that we can actually use, or at least not in the sense that we're talking about it. So these are the equations, pretty basic. A lot of the stuff that the worksheet went through was just plug and chug stuff. Now, there is one extra thing that I want to mention, and it's actually related to work. So it goes back to some of the graphs that were given. Remember, when you're given a graph, you have to choose one of three things with it. You either read the graph to get the answer, you slope the graph, or take the area of the graph. So the question is, if we have a force versus distance graph like this, how would we find the work? If I asked you what the work was moving the object to zero point 0.6 meters, how would you find it? Would you do read, slope, or area? Now, the best way to figure this out, you wouldn't use the equation to calculate it, but you would use it to get an idea of what's going on. The equation's force times distance. This is multiplication. If you think about the three things that I talked about, read, slope, and area, of those three choices, only one of them deals with multiplication, and that's area. So, in order to find the work on a graph like this, you have to take the area. Again, you're not allowed to use an equation, because if you did that, I give you zero point 0.6. If you used 60 newtons times zero point 0.6 meters, you will get the wrong answer. So you have to do area. There's no other way around it. So here it is. We could ask ourselves, we push this car for zero point 0.6 meters. What's the total work? So again, we do the area. We make a triangle shape. The area of a triangle is going to be half base times height. Our base in this case would be 0.6. The height would be 60. So plugging it all in, we do 0.5 times 0.6 times 60, and we get 18 joules. Again, if you just did 60 times 0.6, you would not get the correct answer. All right. So here's the first question. Pause the video work itself. We'll go over in a second. All right, so this question wants us to figure out the work for each of these graphs. So again, work is caused by the area. So this makes a triangle. So we're going to do 1/2 base times height. Plug in the 0.5 and the 8 newtons, and we get 2 joules. For number 2, the shape we make is a rectangle, so that's pretty easy. It's just length times width. So 0.5 times 8, and we get 4 joules. This one is another triangle, so 1/2 base times height again. Same numbers, still 2 joules. And then 4 is another rectangle. This time the width is going to be 4 newtons, and we get 2 joules again. So that's pretty much it. Here's the next question. Pause the video work itself, and we'll go over in a second. Alright, so once again, we want to find the work done. So we're doing area. There's 2 aspects to this. There's a rectangle aspect, where the area is going to be length times width. And then there's the triangle aspect, which is done using 1/2 base times height, as shown there. So when I do these 2 areas, add them together, I get the total amount of work. So I use the numbers that I have. I get that the rectangle part for the first 3 seconds is 18 joules. This part is going to be 9 joules. So altogether, I do about 27 joules of work. From here, we can then figure out other things, but that's something that we'll talk about in some of the later videos. Like I said, everything that we've done so far is really just focusing on the plug and chug aspect, using the equations, trying to get comfortable with the equations. But you'll see in a bit about how we can actually take that these equations one step further. And it's actually something very similar to what we've done in the past. If you have any questions, feel free to let me know. Otherwise, I'll see you later. Good luck and have a great day.